All right, going to take a few minutes to look at a couple of economic analysis approaches that are applied in software development projects. The idea is maybe we have some uncertainty and we've got to maybe come up with a number, an expected values, kind of a weighted average. That's one idea. And the other idea that's even a little deeper and more pervasive is an idea of present value, the idea that maybe money we get in the future or money we have to spend in the future isn't as either valuable in getting or as costly in terms of spending as money is now for a variety of reasons. So this isn't a deep dive in terms of the theory. You had some in your book and other courses, more of a reminder how it applies to projects and maybe a little bit of background so you can, for some assignments that are coming up. So kind of first this idea of, when you're pursuing anything, the outcomes are often uncertain. We don't know exactly what's going to happen when we start a software project. We don't know exactly what's going to happen in a lot of things. And an approach is to come up with what's called the expected value. You might think of a lottery like a pick three, of 10 digits. And maybe the lottery rules are you get $500 if you match all three, and otherwise you get nothing. So, well, what can you expect? Well, what you can expect most of the time is you're out $1, right? Yeah, that's the most often occurring thing. It's the mode and also the medium. But 0.1% of the time, 1 out of 1,000 though, you'll match all three and you'll end up $499 ahead. You get the $500 prize, but you gave them $1 to get in. And 99.9% of the time, you lose $1. And so we average, it's kind of a weighted average, if you will, is what it's called. The term is expected value, but we have the percentage times the value plus the percentage times the value, or the weight times the value, and so it comes up. And so in this particular lottery, which is about typical of like most state lotteries, is you lose 50 cents every time you play. Now, sort of on an expected value term, now let's just talk about lotteries, why you might do them. It doesn't make any business sense, right, to play a game where you're expected to lose 50 cents, expected in terms of average. There's maybe the excitement. Oh, I might get that big prize. Maybe I don't think I will, but there's entertainment value for the fun of it. You might argue that in some lotteries, some of the money anyway goes to a good cause, education, and maybe they get 20 or 30% of that, and the other is for the overhead and like that. I did have a professor one time, so there's something about this variation. He taught decision theory, and I don't know if he made up the story, but he said he was working his way through college and sometimes didn't have enough money to pay the next term's tuition. So he could lay out and work for a term and save money and then have enough money at the end of that. But he could take a small amount of money and maybe gamble with it. It's about the only way to get some of these big outcomes. And if he got lucky, he could win and then pay for next term. And if he didn't get so lucky with it, then, well, he was in the same boat he'd be anyway. So it's a little bit like if something good happens, in this particular lottery, and if we had a total of $500 or $400, that something really exceptional would be happen, then it might be worth, putting that dollar down now, and then it happens. So, there is, it's not quite the same as a game where you lose 50 cents each time around. There's a little bit more going on. But I really wanted to get the idea of a weighted average. And you probably had this in a probability class or something, but, the idea for the expected value in projects or in evaluating outcomes is, first you identify the possible outcomes. They need to be mutually exclusive and exhaustive. Mutually exclusive is, well, we're not overlapping outcomes. You might be talking about, well, we're having this thing and it won't turn out as good if there's rain or snow as if it's sun shining or something. But, bad weather and rain as two outcomes, they're not mutually exclusive, kind of assuming rain is an example of bad weather. You just can't have any overlap. So rain, snow, nice, those might be mutually exclusive. You can measure that's that idea. And exhaustive means you've identified all the possible outcomes that could affect the project. It's going to mean that their probabilities add up to 1, but you've got them all. If you've left out a significant, if we get sleet instead of rain or snow, it's going to be more expensive or not so bad or something. Then that's an important outcome. So exhaustive means we've identified all the possibilities, and we're just going to say those are numbered 1 through M. Then you get some more information you need, the likelihood for each outcome. And the sum needs to be 1 or 100%, since they're exclusive, and we might call those P1 through Pn for probabilities. And then for each outcome, you derive or estimate. Usually it's a monetary value, but something, resulting from each outcome. Okay, if we do this, thing and it rains, it's going to cost X because we, had to give everybody a rain check or something. If it's weather nice, maybe we're going to gain Y because, or another value because, we had the fair or whatever it is. But there's a value that results from each outcome, and the weighted average or expected value is you take the probability times the value plus the probability times the value. Oh, I meant to put another plus sign in there. But you just multiply by the weights and add them up, and it comes up with a weighted average. And then we talk about that as the expected value for the project, and often choose the one if we're looking at multiple projects or ways of doing things or uncertain outcomes. The one maybe with the best expected value is the best one. Okay, and so that's not perfect. There's some variation that goes on here. Back in the other case, winning 500 isn't quite the same as on average, the minus 0.5 or losing $1 most of the time. So, but it's a standard effective way to address uncertainty in outcomes. So what's your kind of delivery on this? In one of your problems, I've asked you to look at this Decker Company, their revenue estimates. This is right out of the book. What they're saying is, well, we are putting in this system and we're going to change the response time in service, but we don't know whether it's going to improve a lot to only 2 hours. I think in the book it was currently 6 hours or something. Or maybe after the system it's only going to improve to 3 hours, or perhaps it's going to improve to 4 hours. But we'd like to come up with, okay, well, what's the value of the project? We're not going to see that result till after we do it. So we go back and we're going to do this estimated value. So, you can read the case, but if the new response time is 2 hours, they can make 20 service calls a week. That's 8 more than they can do now. We make it $150 for each service call. And so this is the increase per week per truck. And then, so we expect if we can get it down to 2 hours, they'd like, we get $600,000 as what we increase our revenue. If, on the other hand, we only reduce it to 3 hours instead of 4, that logic says, well, we'll have a revenue increase of $450,000. And if we only get it down to 4 hours, then we have $300,000 extended revenue. They also give you, so it's, where do these estimates come from? That's where the real hard work comes, crunching the numbers. That's a nice analysis. I make you do it in Excel for presentation purposes and that kind of thing. But the real grist comes, well, where do these numbers come from? For us, they're given. And they expect, they said, well, we think there's a 20% chance we can get it to there, 30% there, 50% to there. So this 20% of this plus 30% of that plus 50% of that, that's these numbers here. And so our expected value, expected revenue increase is 405 all together. It's actually, this 120 is 20% times 600, 30% times this, 50% times that is 405. Okay, and so that's kind of the idea. Now in your spreadsheet, I've asked you to make everything a formula that's that you can, that's possible. So, these are plug numbers, but you can figure out this by taking, this column times this column. So this column should be a formula. this column should be a formula. It's going to be, the average revenue per call times the revenue increase. Okay. Just, by making it a formula, then if values change, you get new information, then your spreadsheet automatically updates. These are just plugged numbers, but this column and this total should be formulas. And then I think in the problem I ask you, well, that's maybe the starting point, and you should be able to reproduce, and you got a good idea of what the answer should be, quote, if your spreadsheet's right. But then, well, what if we could do something like training and change these numbers a little bit? Get this likelihood up and that likelihood down. But we're going to have a new expected value, and that gives you a sense of the value of that extra training program or extra effort. All right, so spreadsheet, doing a weighted average, but this idea of we have uncertainty, and the way we cut through it, and it's a standard and it's got its merits, is to come up with a weighted average or an expected value and talk about like that's what's going to turn out. Though in reality, it's either going to be this or this or this, but that's an average, and we run with that, hoping maybe it's this, and do everything we can, right, to make that happen. All right, that's the first idea, expected value. The second, and probably deeper, and something that really affects even your personal finances and kind of everything we do with money, is this present value concept, okay? And the key principle is that a dollar in the future, right, that somebody pays you or you pay, doesn't have the same worth, okay, than a dollar you have or now, that you have a dollar that you have now or are paid today, right? So if you have it, and you're going to invest it, that's a dollar today. A dollar somebody's promising or you're going to get in a year or 2 years or 3 years is the future. And usually it's discounted. Almost always it's less, okay? In weird situations, probably bad for the economy, like a deflation, maybe a dollar in the future will be worth more. But why is that? Why how a dollar in the future is less? What do you mean by that? Well, there's really three things that come in. One that's playing out now in our economy is inflation, right? If inflation is 8%, about what it's been for the last 2 months on an annual basis, what you realize is on average, what costs a dollar now will cost $1.08 in a year. It's not that everything goes up by 8%. That too is an average. Some things go up more, some things go up less, but on average, next year it'll take $1.08 to buy what I can buy for $1 now. Okay. So somebody gives you $1 in a year, you can't buy as much as you could before. And to figure out, well, okay, how much less am I going to buy? You take 1 divided by 1 plus that inflation rate, and it turns out to be about 93 cents, right? So, and that's what's so insidious about inflation. If it's high and long term, it looks like it's coming down, but we'll see. So if I just have $1 in my pocket now and I don't spend it till next year, I can get 93 cents worth of goods compared to what I could get when I spend it today. And that's one of the reasons they say inflation can be a cycle, because then people realize, well, it's better to spend it today than save it unless I earn, maybe 8% or more interest. We're not about economics and that, but it's why it's a thing. So, one reason that when we look at a project and money that's coming in the future, say, what would I get or what will return later, isn't worth as much. It also turns out, though, if I pay somebody $1 in a year and they haven't gone up because of inflation, right, I'm going to pay them less. I only need 93 cents now to have $1 in the future. So inflation's one reason why future money's less valuable. Opportunity is another one. If I have $1 now, and I could put it somewhere to earn 10%, that would be nice annually, but earn something on it, right? Then I could invest about 91 cents today and have that dollar in a year because I've earned 10% on it. Okay, so $1 next year that I have is really only worth 91 cents today, because if I wanted $1 in a year, I could put 91 cents in that saving, whatever investment, maybe invested in the business, something. There are some I-bonds, saving bonds, that are going about 9%. You have to do them 5 years, and there's some issues there. But again, that gets into finance and accounting about how to actually manage it. But the point to sort of see if you can internalize is, gee, I could put my dollar away, or I could put less than $1 away now and then have a full dollar next year. So somebody, giving me $1 in a year, that's not worth $1. It's worth a little less. And in this particular example, that's 91 cents. Okay. A third big thing that comes into play is risk. Okay. If somebody says, oh, I'll gladly pay you Tuesday for a hamburger today. That was Wimpy from a Popeye cartoon that was actually even old when I was a kid. But something you're promised, well, they just may not pay you back. Maybe they meant to and can't now, or perhaps a project failed or a business closed. A pandemic comes in and the whole world shifts. So whenever you're expecting money in the future, there's a chance that it won't get paid back. And there's some math you can play with 2%. You have to kind of convert it to odds. And so, in the odds, the rate or the discount rate for a 2% chance annually is 0.0204. So just on the chance that if there, and almost is 2% off, it's a little bit more than that. A dollar that somebody promises me in a year where there's a 2% chance they're not going to pay it back is really only worth 98 cents to me today. By calculating almost kind of the weighted average, like I do here, I have a 98% chance of getting $1 in a year and a 2% chance of they're not there. Okay. So the important thing to realize is that in each case, $1 in a year is worth 1 over 1 plus R, for a generic rate where, the discount rate is what R is. And it's inflation, opportunity for gains, odds of no payback, and often it's a combination, right? So, that discount rate is an important thing to estimate. Again, in our examples, they'll tell us, oh, your discount rate is this. In real life, there's it's a little bit of a project or a problem coming up with that. And then you should realize that, with compounding in 2 years, that would be 1 over 1 plus R to the second power, because it's now discounted, for 2 years. I had a 2% chance, of maybe failing in 1 year, and then a 2% chance again of failing in that second year. It discounts in every year by the power n, and you can do compounding things and continuous compounding. Again, that's finance class, cool stuff, not where we're going. What I wanted to do was, if you didn't have it, was have a sense of why they talk about discount. Now, I have you a spreadsheet that you're going to work with. You're actually going to make a spreadsheet to do a slightly different situation from the book, but the principle is the same, and you can use this particular spreadsheet as a starting point. I just kind of wanted to walk through how I did it and some of the formulas. So the key thing here is this is a plugged value, but that's the book calls it NPV ROR, the discount rate. So I think in the original problem, 6% was that combination of how we discount future money for inflation, for opportunity, and for risk, and we feel like we lose 6% every year. What I did here was add a row for NPV factor. Here's year 0, that's kind of now, year 1, year 2, and you can see that this formula here, you can look at it up there, says take this guy divided by 1 plus this discount rate. So it's basically saying in year 1, $1 today is worth 94.3 cents. This compounds it and says $1 in 2 years is worth 89 cents because it applies the same discount to this. In year 3, 84, year 4, we're down to, $1 you're promising me in year 4 is only worth about 80 cents to me now. Back to lotteries, when you win 10 million, they don't give you 10 million all at once. That 10 million is, maybe 500,000 a year for 20 years. And with this discounting thing, that isn't as valuable as 10 million. It's still going to be plenty of money, but it is one of those things that goes on. So in the spreadsheet, it just calculates that. The book kind of talks about all these kinds of things. First look at the benefits of a project, and these were all given. And I put a column here where we have the year one value. Now they do something tricky with the sales. They say, the sales are going to increase annually, okay, by a growth rate that they, in my case, trickily, that happens to be the same as this rate of return. Doesn't have to be. So they say it's going to start out at 500,000, but it's going to grow. We just figured that, that's an estimate. Reduce complaints, we're going to save 70,000 in year one. Okay. But it's not going to grow. That's not going to increase year by year. Reduced inventory benefits are 68,000. That's not going to increase year by year. So, you can look at these formulas, and we'll show you how to get started in yours. So we have benefits then that come every year, right? And that's just summing these benefits. But here's the important thing, the present value of those benefits, right? So, that 638,000 in year one, the value to us now, given this, is only 601,887, and you get that by multiplying this, and you can look at the formula and get there by this, right? And that 668 in 2 years is only worth 594, and the 699,800 in year three. And what we're doing, we're just taking the discount rate, kind of the net factor, okay, for the year, and multiplying by this. So it's nice to have Excel to kind of help you with all that arithmetic. And we say that here it's just adding all these up, but the present value of benefits is really 2,364,000. Instead of the nominal 2,739. So, this is really what we kind of expect. I know in the book they break out development costs, several items, but that has no dynamic year by year to it. So I just left that as a plug number, as a total, and a year zero, is a year zero value, and you can kind of think that's what we invest now, and then we get these returns later. Okay, so I just made that a plug number. No problem with that. It just kind of zeros. I do have a formula there, but it's just nothing there. And then there's the operational costs. So they figure hardware is 50,000 in year one, has no growth rate. So, but it's 50,000 per year. Okay, software is 20,000 per year. Operations labor is 115,000 per year, but it grows at 4%. So people are going to get 4% raises on average, and so that's real money that in the future we're going to have to pay more for those operations folks than we do now in the first year. So that's just a rate of increase applied. But then we do the same thing. Here's this nominal total, just adding all of this up. And then here's this present value total, which says, let's add up all these present values. And so in a lot of ways, these are the real numbers. I call these nominal as you go. So then you can look at benefits, right, or the net benefits, and minus costs, right? So the net is benefits minus costs. So this first one says, let's take that minus that, and it's about 338,000. ROI, your book talks about it, return on investment. It's kind of what we have to do, kind of divided over the total of the first year. So it takes this value divided by 17, the total costs. So we kind of come up with, what percentage return is that. That's a little misleading because that's just nominal numbers. The present value of benefits minus present value of costs shows a truer picture. We're earning a decent but not great 3% on this project, but maybe that still makes it worth doing. Though really, if you could get 5% in a money market or something, this project doesn't make sense on monetary terms, right? Because we're only going to earn 3% in present value if the present value of that return were 5%. But that's just how the analysis goes. And the BEP for break-even point is in the fourth year. Your book shows how you can kind of do that and kind of use this value to kind of figure out where in the 3.8 years or something like that, but it's enough to do it in the fourth year. Break-even point is where do we finally cover our costs and are at least in the black, and that will happen in the fourth year. And you can see for whether we present value it or not. A couple of things I want to show you. I do ask you a question, something like, gosh, what that asks you to do a goal seek or something like that. Something like maybe what, and I'm going to answer the question, what rate of return, NPV rate of return, would result into a present value absolute zero, okay? Meaning if we discount future more than that, we're going to end up negative, but less than that is positive. So we're really kind of thinking what happens, or what you ought to notice is if I change this, okay, how do I fix that? I know it kind of did it in the web for me. And there's probably a way. Now I've downloaded it into Real Excel and enable editing. Okay, so it's the same spreadsheet now in real live Excel. But the benefit of this is, if the rate of return is only 5% discounting, that means future is discounted less, and that makes the net NPV go up because all these nice future benefits, which exceed the future costs, are worth more today. If that's higher, then this goes down. So the question comes, at what value here would make this a zero, that I just absolutely break even? And so there's a what if analysis called Goal Seek. And so you can find it, and here it's, I think you could find it in the menu, but that's a way to do it. I think it's maybe in data and things like that. But it involves a couple of things. You have a cell that you want to set to a particular value. So I want to set E21 to 0 by changing this. And it'll go through an analysis and kind of do some searching and for a minimum point, basically, or a 0 point, trying different values. And we can see that at 7.8%, this project is dead even. At a higher rate of return, discounted rate, we're going to lose money. So that's a piece of information about the project. So if we're pretty sure the NPV ROR is going to be less than 7.8%, we know at least it'll be in the black. If it's possible above that, then not so much. If you do okay, it'll plug that number in. If you do cancel, it'll put the former number there. So I'll show you how that goes. Goal Seek again, and we'll do it. And you don't have to, I'll do the same thing. I want that to set to 0, but you could put, how do I make it 1,000? And then changing that cell. And came up with the same number, but if I do OK, it leaves that in there. All right. So that's a way to use Goal Seek. I think on the thing I have a problem, but that's a way. Once you have the spreadsheet, not only does it make a great kind of a presentation if you're doing this for real, but it's a good way to and look at some what ifs. And I know your problem maybe doesn't have as many rows and that kind of thing, but the nice thing is you can just right click on the front of a row and delete the whole row. And as long as kind of one of the internal rows, then these formulas will still work, and they're pretty straightforward. So what I would do on the assignment is start with this, save a copy, and then change it to your particular problem. All right, and you've got your data course under your belt, so that shouldn't be too much. But of course, as always, reach out with problems or issues. And oh no, there we were. We're on that slide, and I think that's my last slide. All right, take care.